Welcome to the fifth and final lecture of this module on astrophysics of neutron stars. Today, we would talk about the neutron star menagerie, that is the various types of neutron stars we actually observe. Now, we have so far talked about the interior physics of neutron stars. We have talked about phenomenology associated with radio pulsars. Now, today we will talk about various other types of neutron stars. Now, there are about 3000 neutron stars that have been observed in the 50 years since the neutron stars were detected in 1967 by Jocelyn Bell and Anthony Hewish. Now, most of these 3000 neutron stars are actually observed as radio pulsars. So, radio pulsar phenomenology comprises one of the most significant part of neutron star astrophysics, but there are other types of neutron stars which are also very important in trying to understand the physics of neutron stars and associated processes. In particular, neutron stars in binaries, about which you would learn in a future module. Now, here is a summary of various classes of neutron stars in this lecture. Now, let us recall that the most important parameters of a neutron star, intrinsic parameters, are its spin period and its magnetic field. So, here in this picture we have shown observed neutron stars for which some estimate of both the parameters are available in this magnetic field spin period plane. Now, there are, as you can see, different symbols, different colors represent different types of neutron stars. This main island of orange dots, these are the radio pulsars. Now, here you would see it says RPP. So, this means that rotation powered pulsars, and you would recall in previous lectures we have described how a radio pulsar emits. The energy comes from the rotational energy. So, these are rotation powered radio pulsars. The symbol legend GD means these are in the galactic disk. So, these and these objects are in galactic disk, and whereas the black ones, these are in the globular cluster associated with our galaxy. Now, amongst these, the dots correspond to isolated pulsars and the circles correspond to pulsars with a binary companion. Now, then let us talk about these pink objects here. These are neutron stars in a binary, in an X-ray binary, where the companion is a massive star, and these are high mass X-ray binaries. So, they have very long spin periods, reasonably strong magnetic field. So, these are the neutron stars in X-ray binaries. In contrast, there are accreting millisecond X-ray pulsars. So, they are basically neutron stars accreting from a very low mass companion sitting in LMXBs, and those objects are here. Now, you will see very large bars on the magnetic axis. Please note that these are not error bars, but they are limits on the magnetic field measured, or better to say estimated, using different methods. So, the magnetic field measurement in AMXPs is extremely uncertain, and that is signified by this huge uncertainty bars. Then we have the CCOs. These are very few objects, the CCOs, or central compact objects, about which we have discussed in an earlier lecture. They are neutron stars sitting in the center of a recently exploded supernova, and the magnetic fields only have an upper limit estimate, and therefore, these arrows signify that. Then we have INS, that is isolated neutron stars. Now, you would immediately wonder why we are talking about isolated neutron stars separately, because here are these majority of radio pulsars which are isolated. When we say isolated neutron stars specifically in the neutron star community, it basically means that these are isolated, but these are radiating not through their rotation. This is not the rotational energy that is responsible for their energy generation. Instead, we are seeing these neutron stars in X-rays because of the residual heat. And one has to remember, these are very weakly radiating, very dim, and we only see them because they are extremely nearby, and there are only few of them in this class. Then we have something called RRAT, of which we have mentioned in the context of nulling. These are likely rotation powered pulsars, but they are characterized by sporadic single pulses. They do not have regular radio emission pulses like the other normal radio pulsars. Then you have magnetars, which are very interesting. You note that these are the magnetars, and they have extremely high magnetic fields. Now, they are reasonably slow, the spin period is around 1 second, but very strong magnetic field, and therefore, they have very interesting physics associated with them. And there are a couple of radio pulsars which have been marked out, which are extragalactic. By extragalactic, we simply mean that they are seen not in our galaxy, but in either LMC or SMC, which are satellite galaxies to ours. So, here is a classification of neutron star classes. You have already seen that there are large number of observational classes. So, we have tried to classify them in order to understand the physics better. Now, this classification basically depends on the process of energy generation in these neutron stars. So, the first class is of that of rotation powered pulsars, and they are seen in radio, and recent times many of them have been seen in gamma rays, and some of them are also visible in optical, etc. Now, first we have the classical radio pulsars, meaning reasonably high magnetic field, 10 to the power 10, 10 to the power 11 to 10 to the power 13 Gauss, and reasonably slow spin period, about median spin period is about 1 second. Then we have recycled radio pulsars, and why we call them recycled we would explain in a short while. And there we have the millisecond radio pulsars with very fast spin in the millisecond range and shorter magnetic field, and mildly recycled pulsars, which are kind of in between the classical radio pulsars and millisecond radio pulsars. Then you also of course have the rotating radio transients within this category. Then you have accretion powered object. So, the energy that we see coming to us from the neutron star is basically generated by the accretion of material from a binary companion onto the neutron star, and very clearly there are two types of such objects. The one which are sitting in HMXBs, high mass X-ray binaries, and they appear to have high magnetic field, and the other one sitting in LMXBs, they have low magnetic field. The objects that are associated with these two classes are XRP, which are X-ray pulsars, they are pulsars, but emitting in X-rays, and soft X-ray transients. Similarly, for LMXBs, the objects that are associated are accreting millisecond X-ray pulsars and X-ray bursters. So, there are some objects in LMXBs which are not steady pulsars like the AMXPs, instead they show sporadic bursts. Then we have, for want of a better name, objects which are called internal energy objects. Now, they are seen in various frequencies. Why do we call them internal energy objects? Because the source of energy is some process that is happening in the interior of the neutron stars, and none of these processes fall in the broad category of rotation or accretion power, as we have seen before. So, magnetars tops the list in this category, and we suspect that the energy that is coming from the magnetars is because of the decay of its extremely strong magnetic field. We have already talked about the isolated neutron stars and also compact central objects. So, these constitute the broad classification of the neutron star menagerie. Now, let us take a closer look to this classification. Here is a histogram of the spin period of all known radio pulsars. Now, you will see that this has been churned through a Gaussian decomposition mechanism, and we see that the data fits very well if we decompose this into 3 Gaussians. One is our main island of radio pulsars, that is the ordinary radio pulsars. Then there is a small island of millisecond pulsars, and not very surprisingly there is a small hump, there is a small component of intermediate radio pulsars. We will see later how these 3 categories fit neatly into the evolutionary scenario of radio pulsars. Here is trying to see the millisecond radio pulsars clearly. There is a demarcation at the spin period equal to 30 millisecond limit, and this is somewhat arbitrary at the first guess, but if you remember in the previous slide we had shown the spin period histogram, you will see that the clear break to the millisecond pulsar component comes around this spin period. So, we have the isolated ordinary radio pulsars in this island which have magnetic fields 10 to the power 11, and I have included all the magnetars etc. in this definition to up to 10 to the power 15 Gauss, though very strictly the radio pulsars magnetic field goes maybe around 10 to the power 13 or close to 10 to the power 14 Gauss, p order of 1 second. On the other hand, the binary millisecond pulsars, the magnetic field is low, they are here, and the magnetic field ranges from 10 to the power 8 to 10 to the power 10 Gauss, and the spin period is less than 30 milliseconds. Now, amongst the millisecond pulsars, there is something interesting which has been seen recently, that the properties of the millisecond pulsars in the galactic disk and in the globular cluster, they seem to differ a little bit. If you look at the table carefully, you will see that the spin period, which is the average spin period, is given here. The spin periods are similar, though in the galactic disk the spin periods are slightly larger. On the other hand, the magnetic field is larger in galactic globular clusters, and one wonders why the characteristic properties of millisecond pulsars in the globular cluster and the galactic disk vary. There are various other parameters measured out in this column, and one can clearly see that the orbital periods are very different from the cluster objects to the disk objects, and the masses, even though the masses of the companion are similar, the eccentricities are again very different. So, what we have are in the globular cluster, the orbits are much tighter and they are much more eccentric compared to the orbits in the galactic disk. Now, therefore, in summary, we have the averages of the globular cluster compared to the averages in the galactic disk, and the possibilities might be that the cluster millisecond pulsars are younger, or they may have very strong systematic biases, because globular clusters are moving compared to the galactic disk, and sometimes there are contamination from the proper motion of the clusters in the measurement of spin period, and in particular the period derivative, and therefore, the measurement or rather the estimate of the surface magnetic field, or it is possible that they are recycled preferentially with high accretion rate. Now, these are the questions that one tries to answer when one looks at the entirety of the neutron star class, whether they are born with various disparate characteristics or there are various evolutionary links, meaning that all neutron stars are born with an average kind of spin period, average kind of magnetic field, and because of various initial conditions, whether they are in a binary or whether they are in a dense star cluster, their evolutionary pathways differ from each other. Here is a schematic diagram for a neutron star which is accretion powered residing in an HMXB. One can see that this is a very big star in its Roche-Loeb overflow phase, and the accretion disk formed around the neutron star is very small compared to the stellar size. And what we see the emission, it is accretion of ionized plasma channelized by strong magnetic field, and we have these regular pulses similar to the pulses that we have seen in the case of radio pulsars, but these are in X-rays. In comparison, we have in LMXBs, consider the system size here, which is not as large as we have seen in the case of HMXBs, and what we primarily get here are sporadic X-ray bursts. So, this is a typical X-ray burst that you see, and these bursts come from thermonuclear reaction of accreted material on the surface of a neutron star. Now, let us talk a little about the accreting millisecond X-ray pulsars, because we understand these to be just the precursor of radio millisecond pulsars. A neutron star sitting inside an LMXB gets processed, its magnetic field decays, its spin period is reduced, and they turn into radio millisecond pulsars, and what we see in accreting millisecond X-ray pulsars are just before the accretion is turned off in those systems in which they would become radio pulsars. Actually, we have seen systems which are alternating between a very low rate of accretion and no accretion. So, the same object shows up as an accreting millisecond X-ray pulsars, and when the accretion completely stops, it shows up as a radio pulsar. So, we have seen that, and therefore, these objects which are missing links for a long time, people were not sure whether the millisecond pulsars are really generated through binary accretion. So, these are the missing links which confirmed that hypothesis, and therefore, they are very important in the context of neutron star evolutionary pathways. From AMXPs, we see coherent or nearly coherent pulsations in persistent emission. In contrast, from AMXBs or sometimes called XRB, that is accreting millisecond X-ray burster or X-ray burster simply. We see nearly coherent oscillations during type 1 X-ray burst. So, we see oscillations within the bursts, and observations have indicated that the spin period of the neutron stars is the same as the spin period of the oscillations within the burst. Now, the characteristics of these objects, they are transient ultra compact binaries. Orbital period ranges from 40 minutes to about 20 hours. Now, this has been measured only for mainly for AMXPs. Many systems have periods below the minimum period for systems with hydrogen donor, which basically means that they have as companions evolved dwarfs, that is they are not, the companions are not main sequence stars, but they have gone on to the evolved phase, white dwarfs etc. Ultra low mass companions, so these are evolved dwarfs, and the inferred long term m dot, that is accretion rate, and luminosity of the outburst, these are lowest among the LMXPs that we generally know about. So, now let us talk about the evolutionary scenario in particular. Here is a schematic diagram showing how the radio pulsars generally evolve. So, this is called a pulsar's life journey. Young pulsars spin rapidly and possess a strong magnetic field. So, what happens to them? Old pulsars have slower periods and weaker magnetic fields. Now, we have seen that all pulsars, radio pulsars undergo secular spin down, because rotational energy is what is being given out and the pulsars are slowing down. So, they would move like this, and there is also a small amount of magnetic field decay, even though not very strong. Now, the pulsar's emission becomes too weak for us to detect when the spin period increases significantly and the magnetic field decreases. Because if you recall, the radio pulsar emission depends entirely on the generation of a very strong electric field in its magnetosphere because of rotation and the magnetic field, that is a strong magnetic field rotating generates a strong electric field, and that is what is responsible for the radio pulsar emission. So, we can actually estimate a combination for the spin period and the magnetic field beyond which the emission process would not function anymore, and that limit is known as the death line. So, when a radio pulsar in its course of evolution crosses this line, it enters a region which is called the graveyard, where they exist as neutron stars. They still have magnetic field, they still have rotation, but the emission process does not function anymore and they are not visible as pulsars. Now, what happens? We have already talked about them a little more before. If such a dead pulsar is sitting inside a binary, it has a companion, then it gets a rebirth, it gets another chance at being a pulsar again. So, what happens is it gets recycled. If it is sitting in a low mass X-ray binary, it gets recycled to millisecond spin periods, whereas if it is sitting in a high mass X-ray binary, then it gets mildly recycled and it ends up in this region. Now, the question is, why does such a thing happen? It happens because even though the rate of accretion is much higher in HMXBs, the phase, the time duration of active accretion in HMXBs is much smaller than that in the case of low mass X-ray binaries, and therefore, in HMXBs the neutron star does not have enough time to reduce its magnetic field to much lower value or to get spun up to a faster spin period, and therefore, from HMXBs the recycling is only mild. So, this is a schematic diagram showing the radio pulsar recycling. So, here is the normal pulsars and it sort of moves this way and becomes a part of the graveyard. Then if it has a binary companion, it undergoes recycling and appears again as millisecond and binary pulsars. So, in the in between phase they would be visible as X-ray pulsars. If you recall our first slide in which we had shown a number of neutron star X-ray pulsars as members of the HMXBs, you would recall that they had very long spin periods. So, they had actually gone in the graveyard region, but because there is material accretion onto them, they are showing up as X-ray pulsars. So, here is a summary of radio pulsar recycling. The solitary pulsars, excluding the millisecond pulsars, have magnetic fields around 10 to the power 11 to 13 Gauss and spin periods slightly larger. Now, in high mass binary pulsars, that is the products of high mass X-ray binaries, we have neutron stars which are with slightly massive companions and maybe with white dwarfs, and the magnetic field is usually larger than 10 to the power 10 Gauss, and they are coming from high mass X-ray binaries. Whereas, the low mass binary pulsars, that is pulsars with a binary companion which is low mass, have magnetic field from 10 to the power 8 to 10 to the power 10 Gauss, and they are with low mass binary companion less than maybe 0.4 solar mass and very low mass white dwarfs. These are coming from low mass X-ray binaries. Now, here is an example of the ohmic dissipation scenario in low mass X-ray binaries. Now, what you see here is the same magnetic field spin period plane, where we have shown all the different classes of neutron stars, and these tracks basically show you the end product of LMXB evolution for a neutron star. And what you see here, these are for different values of initial magnetic field and then they have evolved. What you see here are these final products do not really generate the millisecond pulsars which have very low magnetic field, and these have been confined at a very high density. The currents supporting the crustal magnetic field have been confined to very high densities, and then you see that they are not really producing the observed millisecond pulsars. Now, we see that after doing this exercise a little bit, we see that the pulsar recycling scenario fits the ohmic dissipation hypothesis very nicely if the crustal currents are mainly concentrated at about 10 to the power 13 grams per cc, which is somewhere in the middle of the crust. Just to complete the story, if the currents are at a very low density, then most of the pulsars would be generated with fields so low that such spin periods are not supported by neutron stars and the magnetic field is very low. Therefore, the emission processes would not work and we would not see them as radio pulsars. Now, in contrast, the ohmic dissipation in HMXBs, they produce objects which are in this region of the spin period magnetic field diagram, and you clearly see that this basically is the same region as the original island of ordinary radio pulsars. So, basically objects from the HMXBs are likely to come in the same region, roughly the same region of the ordinary radio pulsars, which we have seen in the initial plot, histogram plot of the radio pulsars, that the intermediate Gaussian component is very much under the main component of the ordinary radio pulsars. So, the interpretation of all these hypotheses is this, that we have the main island of the ordinary radio pulsars, which we believe are the characteristics of neutron stars with which they are originally born. Then they slow down and no longer act as radio pulsars, they are visible only if they have a companion and sitting in an X-ray binaries, they are then visible as X-ray pulsars. Then if they are sitting in a HMXB, they would be recycled to either this region or maybe around this region, and if they are sitting in an LMXB, then they would be reprocessed or recycled into millisecond radio pulsars. So, this is the kind of scenario, overall scenario of pulsar recycling. We have the radio pulsars and millisecond radio pulsars and long period radio pulsars, and here we have X-ray binaries, HMXBs and LMXBs. So, from HMXBs processed radio pulsars go into intermediate magnetic field objects, and from LMXBs via AMXP we come to millisecond radio pulsars. So, reprocessing in binaries through mass accretion basically achieves this: the magnetic field goes down, the spin period goes down, and the period becomes much more stable. The rate of spin down also goes down significantly. In contrast, we do not really understand the evolutionary links in isolated neutron stars very well. For example, this is the part we really know about. Ordinary radio pulsars, they slow down and they become dead pulsars. We know that, we understand that. Now, in a previous lecture we had talked about nulling pulsars, intermittent pulsars and RRADs. How are they connected, evolutionary connection to the ordinary radio pulsars? They are radio pulsars, but why do they have this peculiar kind of characteristic? Are they evolutionarily connected to something? Now, then we have this very interesting class of neutron stars which are magnetars, and a lot of effort in recent time is going into understanding the physics of magnetars and the nature of its magnetic field and the nature of the evolution of that magnetic field. Now, there is some suggestion that magnetars can have field decay and they may emerge as RRADs or strong field radio pulsars. This connection is not really understood. There is another suggestion that ordinary radio pulsars, when they are born, their field gets buried by hypercritical accretion from the supernova remnant and they come up as central compact objects with very low magnetic field, and after the field re-emerges they might show up as magnetars. They might show up as magnetars or they may show up as ordinary radio pulsars. The understanding is not very clear here. And another aspect that we have discussed in a previous lecture is ordinary radio pulsars undergoing repeated glitches may show up as a magnetar, because some of the repeated glitches are showing some suggestion of magnetic field increase. So, this particular region, this particular area of how those isolated neutron star connect to each other, if there is at all any evolutionary connection between them, is not at all clear. This slide basically summarizes various kinds of suggestions that are now known in the literature, been suggested by various groups of researchers, but there has not been any consensus on this evolution as yet. So, what are the evolutionary links between different classes of neutron stars? This is the sort of understood and established and confirmed link between rotation powered pulsars and the accretion powered objects. So, we have seen how neutron stars are processed in X-ray binaries. This is the connection, and this is the connection between rotation powered pulsars and internal energy objects, which we really do not know yet. And this connection between rotation powered pulsars and internal energy objects come through magnetothermal evolution, on which lot of work is being done currently. So, the questions regarding evolutionary links is, we know that pulsar recycling happen in binaries through accretion and isolated millisecond pulsars, AMXPs, cluster millisecond radio pulsars. There are certain questions that are not answered there, but we more or less understand the overall picture. We do not understand the RRAT connection to any of these. We do not understand whether ordinary rotation powered pulsars and magnetars are connected via a evolutionary channel, whether CCO to magnetar link it really exists or there is no such link, and if there is any glitch induced evolution of the magnetic field. Finally, we would talk about the new areas of neutron star research. Now, any research in astrophysics is dependent upon the kind of observation we can have on this system. Now, from Earth, the two regions of the electromagnetic spectrum which we can look at the sky through is the optical part of the spectrum, that is the visible light, and a little bit into the infrared and ultraviolet, and here is this region of the radio band, and every other region of the electromagnetic spectrum is cut off by the atmosphere. The photons interact with the atmosphere and they undergo certain processes, and they are not available to us to do direct observation of various objects in the sky. For that, we have to depend on satellites, balloon borne experiments, and so on and so forth. Now, neutron stars, as I have mentioned, are mainly observed in the radio as radio pulsars. So, therefore, radio observation is extremely important for neutron star astrophysics. Now, in radio, what we typically started with is a single dish antenna in the radio band, and there the angular resolution that is achieved is given by this formula. The angular resolution theta is dependent on the wavelength of the light that is coming to us and the diameter of the angular aperture of the telescope or the dish. Now, take a typical radio band of which the wavelength is about 1 meter, and let us say the diameter is about 75 meter, that is one of the largest radio telescope in the world, and what we achieve is theta is about 1 degree. Now, what is 1 degree in the sky? You have to remember that 1 degree is the angular size of the sun and the moon. So, therefore, our angular resolution with a single dish radio telescope is rather poor, and in order to observe neutron stars, in order to really understand the physics that is going on around neutron stars, one has to do much better than this, and that we achieve by doing radio interferometry. So, what we have, the multiple elements, we combine the data from a number of radio dishes which are separated by certain distance, and the effective D that we are talking about, the dimension of my radio telescope, if we are doing radio interferometry, then the effective diameter is the distance between these two dishes. Now, we can have a number of such dishes, and then we can have a two-dimensional map of the object in the sky, and we can achieve extremely high sensitivity and can have a very precise image of the object in the sky. Now, there are very large telescopes which have been used to do astrophysical studies of neutron stars, and these are essential for studies of neutron stars, because please remember, neutron stars are very small objects, the dimension is only 10 kilometers. So, you really want to see what is happening near the neutron star, or you want to see processes that are happening very close to the surface, we need extremely high angular resolution. This is very large array in New Mexico, and you see that there are number of radio antenna there, and they are movable along rails, and therefore, the distance between various antenna can be changed, and you can have different kind of resolution. This is our own giant meter wave radio telescope operated by National Center for Radio Astrophysics, which is a center of Tata Institute of Fundamental Research. Now, NCRA is located at Pune, and it operates this telescope, which is 80 kilometers from Pune, located in a village near Narayangaon, and it has 30 dishes, and the largest distance between two antenna is about 25 kilometer, and each antenna has about 45 meter diameter. This is another picture, a very nice picture of GMRT. Now, it operates at a frequency between 150 to 1500 megahertz, and angular resolution achieved is about 2 arc second to 20 arc second, and total collecting area of GMRT is about 45,000 square meter. So, that gives us a very good sensitivity of anything that we observe. Now, the next generation of telescope is of course, the square kilometer array, which is being built in South Africa and Australia, and the expected frequency range in which it will operate, it is 50 to about 14 gigahertz, and the expected angular resolution would be 50 times smaller than the angular resolution achieved by GMRT. So, this is really going to be a new age telescope through which you would have a far better understanding of the universe. So, the location of SKA, this is SKA 1 is the phase 1 of SKA telescope. There would be a second phase in which all the specifications would be upgraded. So, the location is partly in Australia and in Africa. The low and the mid correspond to the frequency range, the lower frequency range and the middle frequency range or the higher frequency range for the moment. The collecting area of these telescopes would be 0.4 square kilometer and the other one would have 33,000 square meter, and these are the number of elements or number of antenna they would have. And the baseline, the maximum distance between two antenna is about 100 kilometers. Now, please remember for GMRT the maximum distance was about 25 kilometer. Now, the current research of neutron star physics concentrate upon the properties of matter, equation of state, mass radius relation, understanding superfluidity which is related to the glitch physics, emission mechanism and understanding the transport properties which is very crucial for magnetothermal evolution. And there is the new aspect of astrophysics in the recent times which relates to the gravitational physics. Now, neutron stars are sources of gravitational waves. So, it generates gravitational waves and it can also detect gravitational waves through pulsar timing arrays as we have discussed before. And there are plasma processes which are happening in the magnetosphere of neutron star and general relativity can be important there. So, there is a huge amount of gravitational physics that is related to neutron stars, and this is one major area of recent research that people are being involved in. Now, let us consider the gravitational wave detectors for a moment. What we have, there are different kinds of detectors which would scan different frequency of gravitational waves, and if you note that the sources that will generate them are also different. So, different sources will generate gravitational waves at different frequency. They also correspond to different ages of the universe and there are different kinds of detectors. So, now where are the neutron stars? Here are the neutron stars as sources, here and here. So, the compact binary, that is neutron stars and black hole, their merger can generate neutron star can generate gravitational waves in these frequency ranges, and these are detectable by terrestrial ground based observatories, also space based gravitational wave observatories. On the other hand, here is quantum fluctuations in the early universe, the stochastic background which gives nanohertz gravitational waves, and those can be detected by pulsar timing arrays, for which we would on the other hand require the radio telescopes that I have been talking about in this past few minutes. Now, as sources of gravitational waves, neutron stars can be transient sources of gravitational waves through binary in spiral neutron star or neutron star black hole binary, and we have already detected neutron star binaries through our terrestrial ground based gravitational wave detectors, and I have mentioned certain significant results from neutron star binary merger process in a previous lecture. Now, Neutron stars can also be very good sources for continuous gravitational waves. Now, the advantage of having continuous gravitational waves is then we are not time bound to observe a transient phenomenon. We can target our observation, we can observe a particular system for a long time and can get valuable information about the system as well as the nature of gravitational wave itself. So, rotating neutron stars are best bet for observing a continuous source of gravitational waves. Now, there could be tidal deformation in X-ray binaries, or there could be surface inhomogeneities in neutron star surface. So, these are certain examples of how we can have continuous gravitational wave from rotating neutron stars. Now, in isolated neutron stars we can have surface deformities, and the surface deformity will give rise to gravitational waves which will give fractional change in length, that is the amplitude that one would detect in the observatory which is either ground based or space based, and that depends, this is a formula for fractional change in length, and this very strongly depends on the mass quadrupole moment, the amount of mass quadrupole moment that the neutron star may inherently have, the distance to the neutron star and the spin period of the neutron star. Now, we notice that there have been some suggestions about surface inhomogeneities of neutron star giving rise to gravitational waves. What we have seen is the amount of mass that would be available for surface inhomogeneities are very small. So, this was the original estimate of 10 to the power minus 25 solar mass. Modern estimates of crustal strength etcetera have upgraded the number significantly, but even then it is very small. So, ordinary surface mountains, that are surface inhomogeneities, are incapable of producing gravitational waves that would be easily detectable by our ground based observatory or even the space based observatories that are being planned today. Then there is another kind of surface inhomogeneity one can think of, accretion columns on accreting neutron stars. Here the height of the mountain would basically depend on the strength of the magnetic field, and we expect that that would give a neutron star a much larger mass quadrupole moment, which would give us a larger amplitude of the gravitational wave generated, but would it still be detectable by the observatories in near future. It appears that that may not be so. Here is a diagram of various detector sensitivities. Look at here are the ground based observatories, the Virgo, the LIGO, and here are some of the space based observatories that are being planned today, and this is the entire range through which neutron stars, whether isolated or binary, can act as stable continuous source of gravitational waves. Now, what we see is in this picture that this is the region in which our planned detectors, space based detectors sensitivity lies. So, this is the spin period and magnetic field plane of neutron stars, where you see all these neutron stars. If we now try to see where the detection limit of the observatories, gravitational wave observatories would be, we see that they are in this corner where there are no neutron stars that we know about. Now, here is this in this box what you see are strongly magnetized objects which are the magnetars. Now, there is some suggestion that magnetars are born extremely rapidly spinning. If that is so, then this box would be shifted to a region like this, to the region B. Now, this region is accessible by the detectors that are being planned today. Now, if magnetars are born spinning very fast, on top of that if they are sitting in an HMXB where accretion column heights would be largest, then we can have strongly magnetized very fast neutron stars in HMXBs. Gravitational wave generated by such objects might be detectable by the space based detectors not too very far from us in time. There has been some suggestion that such cases might indeed be plausible sources of gravitational wave detection, and if that happens, that would herald a new age in gravitational wave physics in detecting continuous sources of gravitational wave. Now, before finishing my lectures, I would like to mention that in order to understand all the facets of the neutron star, we need to understand neutron star behavior in high energy regime, and the high energy regime which is most important for the physics of neutron star is the X-ray regime. As we have already said that neutron star processing happens in low mass X-ray binaries and high mass X-ray binaries, and the evolutionary processes are very much dependent on what is happening in these X-ray binaries. So, this is India's first multi wavelength space observatory ASTROSAT, which is dedicated to observations in astronomy, and this has various detectors on board: the large area X-ray proportional counter, the soft X-ray telescope, and various other instruments which will observe objects in the sky at high energy regime. And there have already been very interesting results in the area of neutron stars which have come up from the data taken by ASTROSAT, and we are hoping that this would shed new light in our understanding of neutron stars. So, here are some resources for you to learn about neutron star and understand the physics in more detail. So, these are some books which have been listed, and here is a list of neutron star databases where you would find current data from various observatories in different energy bands, and you can actually go to these databases, download the data, and can devise your own little projects, and maybe that would help you understand the physics even better. Thank you very much.